Hello, do you hear me?
Yes.
Yes, maybe we can start. So welcome everybody to this week's Majorana-Raychaudhuri seminar series. Today's first speaker is Joao Rosa from University Coimbra, Portugal, and he's going to talk about primordial black holes in string axiverse. So maybe I'll send a reminder when 5 minutes are left.
Okay. Okay. Well, thank you very much, Anish, for the kind invitation to give a seminar here for your series. So today I'm going to talk about a little bit about the work I've been doing in the past 2 or 3 years about putting together primordial black holes and string axions. And this is work mainly done with Marco, who is also in Zoom, I think. He was my former PhD student, and also with John Match Russell, and one of the works that I'm going to talk about also with a master student, Philippe Serren. So, primordial black holes, it's quite an old proposal, goes back to Hawking in the 1970s. And the idea is that in the early universe, if you have large enough density perturbations, let's say order 1 or above a certain threshold, when they become smaller than the Hubble horizon, they will directly collapse and form a black hole. And I think most scenarios will form primordial black holes. You just need to have order 1 density perturbations. So the question is not really if they form, but if they form in large enough numbers. And the issue is that we know that inflation is supposed to generate these density perturbations. And on the large scales that we see in the CMB, they're very small. But they're Gaussian in principle, so there's a tail in the distribution that will generate some primordial black holes, but maybe not in large enough numbers. However, there are some non-standard inflation models involving more than one field, for example. There are scenarios with phase transitions, and actually quite a lot that I'm not going to discuss, but there's this nice recent review by Escrivá and Connell that reviews these scenarios that predict the formation of these primordial black holes in large enough numbers that they could be interesting for cosmology. And you can see here that I put here the plot from this review where you have the constraints, the present constraints on the fraction of dark matter in the form of these primordial black holes. And you can see that they can form with a very broad, in a very broad mass range, whereas astrophysical black holes have to be above the solar mass. You can have much lighter black holes here. And one of the things that have made people interested in primordial black holes in the past few years is this window here, where it's called the asteroid mass window, where in principle these primordial black holes could account for the whole of dark matter. And they are very attractive dark matter candidates because, well, they're very, very dark. They behave as cold, non-relativistic particles for all practical purposes. And in fact, people have argued that black holes are the only dark matter candidate that we actually know exist. We don't know if primordial black holes exist, but certainly we know that black holes should be around. So it's interesting to pursue this idea. There's also other windows that, from where we have interesting hints that primordial black holes might actually exist. One of them is here in around this mass scale, where you have constraints from microlensing, gravitational microlensing. And there's this one experiment called OGLE that has seen a few, I think it was 5 or 6, microlensing events with a very short duration, which can only be accounted for by some compact objects with a mass close to that of planets. So people have argued that probably the easiest explanation is that they're just freely floating planets. We don't see the stars around them. And planetary formation scenarios, they do predict that some planets get ejected from their stellar systems, but they might not be in large enough numbers. It's not expected to explain these few events that OGLE has seen. So the one proposal that has been around that these are planetary mass primordial black holes with around 1% or a few percent of the dark matter density. Also, people have proposed that some of the binary black hole mergers that LIGO and Virgo and CAGRA have detected in the past few years actually might have a primordial origin as well, especially because the black holes in these binaries seem to have very low spins. And that's actually it's predicted for black holes that form in the early radiation-dominated era where the gravitational collapse is almost spherical, so you don't generate a large spin for these black holes. So there's lots of interesting hints for the existence, but for this talk, I'm actually more interested. I hope you can see my pointer. I'm more interested here in
Yes,
this.
we can.
Yeah. Okay, good. And yeah, please feel free to interrupt me when if you have any question I forgot to say. I'm interested more in this region here, which is actually quite the most constrained one, because these are the primordial black holes with masses around 10 to the 15 grams or 10 to the 12 kilograms that are evaporating today. So that they're in the last stages of their evaporation process, and I'm going to talk more about this. So they're quite constrained in terms of their abundance because the Hawking emission leads to photons, and these contribute to the extragalactic gamma ray background, and we have very good measurements of that. So they can only account for like 10 to the minus 7, you can't even see it here, or 10 to the minus 8 even of the dark matter density. So they seem that it doesn't seem to be the most promising window, but actually if you take into account that there's loads of dark matter around us and that these objects should have the typical velocities with respect to us of around 200, 300 kilometers per second, they're typical of dark matter particles. You can convert this into a flux, and you see that you can expect like at least one primordial black hole per milliparsec squared per year. So we could, in principle, if we have ways to detect these black holes, and I'm going to talk more about this towards the end, we could expect to have one of these primordial black holes coming within a milliparsec of the Earth within the lifetime of a typical experiment of a few years. Why am I interested in these black holes? Because of Hawking emission, essentially. So this is also an effect that Hawking predicted using essentially a semi-classical approach of quantum field theory in curved space. And in a nutshell, the idea is that whenever you have matter collapsing into a black hole, at past infinity, the quantum fields should be in the vacuum state in principle, but this does not coincide with the state that an observer at future infinity sees. And actually, Hawking showed that the state that is measured by this distant observer is actually nearly thermal states. So you can associate a temperature with the black hole, which is called the Hawking temperature. And this is proportional to the surface gravity. And for non-spinning black holes, it's inversely proportional to the black hole's mass. So I put here some typical numbers for the mass range I'm interested in for these primordial black holes. This temperature is quite high, it's around 10 MeVs, whereas for stellar mass black holes, this is very small. So an interesting thing about these light primordial black holes is that they have quite significant Hawking temperatures. So you basically can expect them to emit all particles in nature below this MeV scale. This is the expression for the particle emission spectrum here. It has a kind of Bose-Einstein or Fermi-Dirac form, except for these gamma factors, which are known as the gray body factors. And I'm not going to explain them in too much detail. I can tell you more about it if you want. But essentially, they're the consequences of the waves that are going to infinity. They feel a non-trivial potential created by the black hole itself, and they have to tunnel through this potential. And so the probability of escaping to infinity and being detected is not exactly 1. So these are called gray body factors because they deviate from the usual black body form. And here omega, the capital omega, is the rotational velocity or the angular velocity of the black hole at the horizon. It's going to play an important role later on. So as the black hole emits particles, they take away the black hole's mass and its spin. So you have these simple differential equations. You have to compute these f and g functions. They're only functions of the black hole spin parameter, which I wrote here, a tilde between 0 and 1. So 0 is Schwarzschild, 1 is an extremal black hole. And you can compute them basically by integrating over all the frequencies of the modes that associated with each field. So you have an LM decomposition of the modes, and I here stands for the particle species. So you integrate over all of this, taking into account the energy that each mode takes, it removes mass, and the angular momentum that each mode takes, and it removes spin. So thinking just about the Schwarzschild black holes, you can integrate the mass equation here. And if you take into account just the particles in the standard model, that these black holes can emit, you find that the evaporation time, so the time until the black hole vanishes, in principle, we don't know if it vanishes completely, but just with using this semi-classical approach, it would take for a black hole of 5 × 10⁻11 kilograms in that rough that mass window I mentioned, it would take 14 gigayears for it to evaporate. So close to the age of the universe, and as I mentioned earlier. That's why I'm going to focus on the black hole masses around this mass scale. The standard law, so this is just mass, is that the black holes spin down as they evaporate. And this is true, as I'll explain, in the standard model. Basically, they lose spin faster than they lose mass. So they quickly become Schwarzschild black holes. So the standard law has been that spin is not important for this evaporation business. And I want to argue that this is not necessarily the case when you take into account that the fundamental theory of nature might be a string theory. And yes, because essentially, as I said, the black hole will emit all particles that exist in nature as long as the Hawking temperature exceeds their mass, or otherwise the emission is just Boltzmann suppressed by these exponential factors. So what's special about string theory? Well, quite a few things. It is a theory that must have 6 compact extra dimensions, because it has 10 dimensions and we only perceive 4 of them. So you need to have a compactification and do a dimensional reduction of all the fields that you have in the theory. And the other thing special is that they have in the closed string spectrum and also in the open string spectrum, you have new states. They're called p-form fields. They're essentially tensor fields. They call the Neves-Schwarz, NS, and Ramon-Ramon, RR, form fields. And when you compactify them, they lead to scalar fields. So here's an example of the Neves-Schwarz 2 form. It's an antisymmetric tensor, B mu nu. And when you can do this dimensional reduction, what you do is you expand this in terms of the bases of antisymmetric tensor fields in the 6 compact extra dimensions that I'm denoting as Y. And the coefficients depend on X, our 3+1 dimension, so they're scalar fields. And so you're going to have as many scalar fields as the dimension of this basis of 2 forms of antisymmetric tensor fields. And this is dual to the number of closed 2 cycles that you have. So essentially, the number of axions that you get in your 4 dimensions is as many as the number of compact cycles that you have in the 6 extra dimensions. This is for 2 cycles, but other fields involve other cycles. And just from combinatorics, because you have 6 extra dimensions, you have a large number of these scalar fields in your 4-dimensional theory. Why do we call them axions? Because these tensor fields, they have gauge symmetries in the 10 dimensions. And these scalar fields, they inherit shift symmetries, perturbative shift symmetries from these underlying gauge symmetries. So they have shift symmetries like the axions that forbid mass terms at tree level. In principle, but they can get masses from non-perturbative effects, and they're typically exponentially small. So string theory can predict, in particular, the QCD axion, which has been proposed as a solution to the strong CP problem. There are some technical issues because you need to stabilize the extra dimensions. It's called moduli stabilization. So depending on how you do this, you can actually give masses to all the axions. But the argument that Arvanitaki et al. Gave in 2010 is that if you assume there is one QCD axion, you have to get rid of all these effects that give large masses to axions. You're left with only the non-perturbative effects. So for most axions, and we're talking order 100 or 1,000, the masses of these axions will be extremely small. So bottom line is this idea of the string axiverse is that in realistic string compactifications that include at least one axion to solve the strong CP problem, you expect order 100, 1,000, and potentially even more depending on the geometry of your compact extra dimensions of these axion-like fields. And scalar particles are very different from other particles in terms of how they might influence the evaporation of a black hole. And this is a result that goes back also to 1997, 98 by Taylor, Chambers, and Hiscock that studied what happens when a black hole evaporates through scalar emission. So here's a plot showing how the black hole spin is what I called A tilde earlier between 0 and 1 evolves as a black hole evaporates and emitting only spin 1/2 or spin 1 or spin 2 particles. And here's the scalar case. And they have two cases. Here you start with a near extremal black hole and you see it spins down. And here you start with a black hole, a very low spin, and you see that it spins up. The reason for this behavior, which is distinct from the other higher spin particles, is that scalar fields are the only ones that can be emitted without taking away any angular momentum from the black hole. Because they have S equals 0, so L, the orbital angular momentum, can also be 0. So they can be emitted without removing angular momentum from the black hole. There are also other modes. So there's L equals 1, L equals 2, and so on. But for small spins, and this means below 0.55 for pure scalar emission, the L equals 0 mode dominates. So the black hole spins up. If you start above 0.555, then the higher modes, L equals 1 and so on, dominate, and the black hole spins down. But you see, most particles in the standard model are fermions or gauge bosons. So if you put things together, a black hole does spin down as it evaporates, and that's the standard law. But now if you have scalar particles, that does not need to be the case. So we wanted to put these two things together, the axiverse and this idea that you have many, many axions in string theory with this observation by Taylor-Chambers and Hiscock that a black hole can spin up. So we computed the Raychaudhuri trajectory, so how the black hole spin and mass evolve. And this is given by this combination of the G and F loss rates that I have earlier, this H function, which I plotted here for different spins. And you can see that the scalar case, this purple curve here, is the only one that has, for each H has a 0, which means that it can go to a finite value of spin through evaporation. So what we did is we studied numerically the dynamics of an evaporating black hole, where we considered all the standard model particles and a graviton, a spin-2 graviton, but we added an arbitrary number of light axions with masses below the Hawking temperature of the initial Hawking temperature of these black holes. And the way we did it is that we essentially treated particles as massless. It's an approximation, but it's a good one. If their mass is below the Hawking temperature, and if the mass is above the Hawking temperature, we simply did not include when computing the F and G functions, which we did numerically. So as the black hole evaporates, it loses mass, the Hawking temperature increases, so we have to take into account more and more particles of the standard model. There's some technical issues about how you include QCD states. So we include pions below the QCD scale, but above the QCD scale, you start including quarks and gluons as free particles, as expected from deconfinement. So let me just show you we obtained the results in these two plots. And what I'm showing here is actually the present mass of these primordial black holes and the present spin. So this is a kind of a photograph of what we expected today after they have evaporated. So most of them, they will start with masses around 10 to the 12 kilograms, and they will evaporate, and they will be at different stages of the evaporation process today. And so here, each curve corresponds to a different number of light axions, between 100 and 1,000. We also included 10,000. And you see that if we start with a very low spin, as expected for black holes formed in the radiation era, if you don't have any axions, this is the black curve, the black holes just spin down. So we don't expect to see any light black holes today with spin. Whereas if you have hundreds of axions, the black hole actually spins up. The more axions you have, the more it spins up. And it's a competition between the number of axions we include and the number of fermions and gauge bosons. And the fermions and gauge bosons, especially the QCD quarks and gluons, they become relevant for when the black holes reach around these masses and the Hawking temperature goes above the GeV scale. So eventually, in some cases, the black hole spins down again due to the quarks and gluons. But still, you see that it's a very different expectation for primordial black holes that evaporate within the string axiverse or just in the standard model, is that we can expect to have some black holes with spin today. So we also did the same kind of simulation, starting with a high value of spin. and you can see that the axion emission delays the spin down of the black hole. We can see this as an evolution, time evolution, if you want, from right to left. So they lose mass as they evaporate. But the general expectation is that we're going to have light black hole remnants with masses like 10 to the 11, 10 to the 10, 10 to the 9, and they have some detectable, some measurable spin. Whereas if there are no axions in the game, then all these black holes should be essentially Schwarzschild spin zero. So conclusions about this is that, well, the present mass spin distribution of these black holes can give us information about the full number of light axions, so the whole of the string axiverse, or at least a very large fraction of the light axions. We have lots of probes of the string axiverse in different mass ranges, but not really one that probes the whole string axiverse. And since this is only a purely gravitational effect, this doesn't really care about how these axions interact with the standard model particles. And it's actually, we don't need, it would be nice if we could find black holes at these different stages of the evaporation process, which might be hard. But even just finding only a few spinning black holes in this that have evaporated a little bit at least, so 10 to the 9, 10 to the 11 kilograms, would be a smoking gun for at least 100 or 200 axions. And so really a smoking gun from the axiverse. We checked that, I mean, these black holes, they merge, or these masses, they merge very rarely. This could affect the spin distribution, but not for these masses. And also an important thing to say is that the limits on the PBH abundance in this mass range, if we take into account axion emission, are relaxed, because the black holes that are evaporating today were born with slightly larger mass than in the standard model, because they spend most of the age of the universe just emitting more axions than anything else. Another important consequence of this is that you basically have all these primordial black holes around. They're emitting lots of relativistic or hot axions. So, and here's just to have an idea of the number of axions you expect from each primordial black hole is quite large when you reach these masses. And we estimated that the number of the axion density, the hot axion population that should be lying around, can even exceed the density of the cosmic microwave background. So it's a new population of hot axions, very different from what might be produced cosmologically through other means. So it's interesting for axion detection as well. Now, another important consequence of having black holes spinning up due to evaporation is that they can trigger superradiance. So let me review superradiance. I'm not sure if people are familiar with this. So superradiance is an amplification phenomenon common to many physical systems, and Zeldovich in 1966 proposed that it should be the case, it should occur for rotating Kerr black holes. And the idea is that if you have a wave impinging on a black hole spacetime, it's a scattering process, will get reflected. But if the frequency is low enough, below a multiple of this rotational angular velocity of the black hole, the reflection coefficient can be greater than 1, so the waves are amplified. So it's an amplification process. That's what's called superradiance. And Press and Tucholsky, back in the 1970s, they made this thought experiment of surrounding the black hole with a mirror so that you could confine these waves. So they would scatter back and forth and be amplified multiple times. So it gives kind of an instability effect that they call the black hole bomb, because at some point the radiation pressure will be so large within this mirror that the thing would in principle explode. But we don't really need a mirror. That's kind of a thought experiment. You just need to confine the waves. And fortunately, nature provides us with a way to confine waves, which is looking at massive waves or massive fields, because they feel a non-trivial potential in the black hole's space-time. And in particular, there's a potential, well, as a result of the basically gravitational potential of the black hole and the angular momentum barrier. So you can create bound states. So the bound states in a black hole spacetime, their time dependence is the usual harmonic dependence, but the frequencies, they are complex numbers. And if in particular, as you can see here, if the imaginary part of the frequency is positive, the fields, in this case a scalar field, would be amplified exponentially fast. This means essentially that the occupation numbers of these bound states are growing exponentially. And if you can compute these frequencies for these bound states in this potential well, because it's a 1 over R potential, it's not surprising that the spectrum has a hydrogen-like form. So sometimes they're called gravitational atoms. So here's the expression of the real part of the frequency is the mass of your field, I'm calling mu. And there's a binding energy, which has a similar form to hydrogen spectrum with modes NLM, where the role of the fine structure constant alpha is played by this dimensionless mass coupling, which is a product of the mass of the field mu, the mass of the black hole m, and normalized by the Planck mass squared. So if this is small, you get this hydrogen-like spectrum form, and you can show that the imaginary part of the frequency is proportional to this combination omega minus m omega. So for low frequencies, this is negative, so the whole thing is positive, and you do have an instability, an exponential amplification of the bound states, of the occupation numbers. You can see that this is proportional to a large power of alpha, so the mass of the fields. So the fastest growing mode, it has to have some angular momentum because m is the angular momentum number, is in atomic notation, the 2p mode, or 211 states. And you can compute the growth rate, and it's approximately given by this expression here, where basically the spin parameter of the black hole comes from the angular velocity, and the alpha comes from replacing the real part of the frequency with just the mass. So you see that if the spin of the black hole exceeds the 4 alpha threshold in this approximation, this is going to be positive, and the states are going to be amplified exponentially fast. If the spin is below, then this is negative, and the state decays. So this is both an amplification and an absorption process by the black hole. But if there's amplification, then you can build these what we call superradiant clouds around the black hole. The typical size is just given by the Bohr radius, and they're called R0. So for GeV particles, this would be around the Fermi scale. So they're like very small things. And the idea that we explored with Marco Calza and Felipe Serrano was that, okay, in the axiverse, the black holes can start with a very low spin, so no superradiance, but then evaporation will make them spin up. So this, in principle, could trigger superradiance. But it can't trigger superradiance for very light axions, simply because of this large power of alpha. So if you have a very light axion, mu is very small, alpha is going to be very small, and this process is too slow. It means that superradiance would only make these clouds grow on time scales longer than the age of the universe. But this can happen if we have axions with masses above the MeV scale. I told you that in the string axiverse, we have loads of axions with very exponentially small masses, but they're exponentially small compared to a high energy scale, typically the string scale or the supersymmetry breaking scale. So in principle, you could expect that there are at least a few axions with masses above the MeV. So we studied what happened in this case. So we modified the equations I showed you before for the mass and spin evolution of the black hole to account for the formation of these, let me call it heavy axion clouds. So removing mass and spin from the black hole as the clouds grow. And here's the equation for the number of axions within this cloud. So here's some results. So the dotted lines here correspond to the Raychaudhuri trajectories in the mass and spin. So as the black hole evaporates, it would just spin up with 400 light axions in the spectrum, 700, and here's just a case with 100. And the dashed line shows the superradiance threshold for an axion with 100 MeV mass. And you see that these are the solid lines. As soon as the black hole starts spinning up through the Hawking emission with hundreds of light scalars, and then it hits the superradiance threshold. And when it does so, I show here what happens on these plots. The number of axions in these superradiant clouds, the 100 MeV axions, it just grows exponentially fast. It decreases the spin of the black hole until it hits the superradiance threshold. So omega equals m omega. So the cloud no longer grows. But there's an interesting effect because superradiance is extracting spin from the black hole, but the Hawking emission is still trying to spin it up. So these two effects compensate and keep the spin parameter nearly constant, and they keep producing axions in the cloud to extract the additional spin the evaporation is trying to give. So you still have some growth of the cloud after this first saturation. But an interesting thing is that superradiance is faster than evaporation, and the net result is that the redshift trajectory just follows the superradiance threshold. So we expect, in this case, to have these peaked mass spin distributions for primordial black hole remnants today. So black holes with masses lighter than 10 to the 12 that have evaporated, you should have a peaked mass spin distribution. And the interesting point is this peak here depends on how many light axions we have driving the evaporation and what is the mass of the heavy axion, which will undergo the superradiant instability. So we looked at the dependence of this critical mass maximum spin on the number of light axions below the MeV scale and on the mass of the heavy axion. And you can see that if we find this peak in the distribution, this critical spin, we would learn not only how many light axions we have, but also the mass of this heavy axion, which is quite interesting. Also, in principle, all axions can in principle decay into two photons because they have these Chern-Simons kind of gauge couplings to all gauge bosons. So a heavy axion would in principle decay. So we computed the decay rates. And so we expect a line essentially from the decay of an axion to two photons. So a 100 MeV axion, for example, would decay into 50 MeV photons. They're almost at rest. And we superimpose this on the Hawking emission spectrum, so the photon spectrum. I'll discuss the spectrum in more detail later on. But the point here is that you see that even for a very small axion-photon coupling, which is typical of string axions, we would see kind of this small bump in the Hawking, in the photon emission spectrum of a black hole, which would be the signal of having this heavy axion cloud that forms through superradiance around it. So it would be a potential way of directly observing these superradiant clouds and knowing whether there is a heavy axion with a certain mass. Now, this is an interesting, but let's go back to the case where no heavy axions occur in the spectrum. And there's still something interesting that me and Marco, we have explored recently, which is the fact that as the black hole evaporates, the Hawking temperature increases. So at some points, it will hit temperatures above the TeV scale, so beyond what we can currently probe at the LHC or other colliders. And this means that the primordial black holes will start emitting new particle species that we haven't seen in their final seconds of existence. And this has already been studied by Baker and Tam in a couple of papers. This speeds up evaporation because you're emitting more species. So if you track the evaporation in this final stage, you can in principle identify the existence of new particle species. But we have something different in the axiverse because the black holes not only lose mass, but they also, the spin could change and they could spin up. So we tried to see what kind of information we could get from the black hole spin in this axiverse picture. So here's an example of one of our evolutions with 400 light axions in the spectrum and the standard model particle content. So 4 Higgs scalars, 45 fermions in the 3 generations, 12 gauge bosons. And here, no spin 3/2 particles. And you see the evolution, it spins up. And I put here the remaining lifetime of the black hole. So the age of the universe, where it starts, 1 million years, 100 years. This is where you hit temperatures above the QCD scale. It starts spinning down 1 year, 1 day, 1 hour, 1 minute. And this is where you hit the TeV scale. So we don't know what happens. So we just try to see what happens if we added, as a toy model, new physics at 5 TeV scale, which is beyond what we can currently probe with the LHC. So here's what happens with different curves in the redshift trajectory of the black holes. If we add, for example, all the particles in the MSSM with the same mass, so the minimal supersymmetric standard model, so you have to add scalar partners to the fermions and fermion partners, the gauge genius to the gauge bosons and so on, alongside our axion. So you see that there's a modification. It spins down slightly faster. Another example, which is the green line here, we call HS, is a hidden sector. It's essentially a full copy of the standard model, 180 degrees of 18 degrees of freedom. for simplicity, all at 5 TeV. But in this case, we're not adding many scalars, we're adding more fermions, and you see that it spins down even more quickly because we're adding more fermions. And an even greater effect happens if we allow the superpartners of the axions, of the 400 axions, these are the axinos, they're fermions, and the saxions, which are also scalars. If we add them into the game at 5 TeV, the black hole will spin down even more quickly. But you see, if we can track these trajectories, we could identify these different extensions of the standard model. So this is something that having spin allows you to do. So we went a bit further. So if we could track the mass and spin of the black hole as a function of time, we can determine the mass loss and spin loss rates, the F and G functions, potentially their derivatives, and they're linear functions of the number of spin 0, spin a half, spin 1, and spin 3/2 particles. We could have gravitinos and supersymmetric models. So here's an example of what happens to these functions if we could measure them experimentally for the standard model in blue, for the MSSM in red, and for the hidden sector in green. And you see the behavior of these different extensions of the standard model is quite different. But if it means if we know this matrix is known theoretically, the contribution to these F and G functions from each type of particle. So if we could measure these experimentally, we could invert this and know exactly how many scalar particles, fermions, gauge bosons, spin 3/2 particles we have. So it's kind of a powerful thing if we could detect these black holes and track the final seconds of their evolution. A potential problem, of course, you see here the F function is pretty flat, so measuring its derivative might be a challenge. It's actually a consequence of a cancellation from the contribution of scalar and non-scalar particles that have opposite signs. And a potential solution would be to try and measure the second derivative of the G function, which is the angular momentum loss rate. This has a slope and a curvature that we could see, so it's a potential way of measuring this. How much time do I have? Anish, sorry. Anish?
Yes,
Yeah.
yes. So sorry, just a connection. Yes, so we still have about 10 minutes.
Oh, okay. So it still gives me,
minutes.
okay, it still gives me enough time. So you've seen if you measure the mass and spin of these primordial black holes, the remnants that we see today of the evaporation process, we could see lots of things. We can know the number of light axions, whether we have heavy axions, or we can even probe new physics beyond the TeV scale. But all this relies on being able to measure the mass and spin of the black hole. So part of the effort that we've been doing is also trying to understand how we can extract these properties if we detect the black holes. The idea is that we would detect these evaporating black holes from their Hawking emission spectrum, from the photons they emit. In our first paper with John March Russell, we just observed that this is the nearly black body spectrum for black holes with different masses. So you see lighter black holes, they peak at higher energies because they have a larger Hawking temperature. And you can see the effects of having spin. So having from 0, 0.2, and up to 0.5, you see that it increases the height of this peak. So if we know the distance to the black hole we are detecting with this spectrum, we can measure measure the flux that we obtain at the Earth. We can, in principle, compare with this total amplitude and know if the black hole has some spin and know its mass from the position of the peak. So this requires measuring the distance to the primordial black hole. And typically, if they are within milliparsecs or even parsec scales, in principle, you can do this using parallax measurements. But we wanted to go a bit further and see if we could do something that would be independent of the black hole mass. So a second proposal was actually looking at the full spectrum, and I should explain what I mean by the full spectrum, because the black hole emits all kinds of particles. So it emits directly photons. These have the black body shape that I'm showing in this example here with these lighter lines. But it also emits secondary photons, because it emits, for example, electrons and muons. They're charged particles and they're accelerated as they move away from the black hole. So they radiate photons, and these are the secondary photons. There are also photons from pion decay, for example. So they create the secondary spectrum. And you see that these are photons with lower energies because they're radiated from the primary particles. So you can still see the primary peaks here, but there's the secondary parts. So we looked at we used Black Hawk. It's a publicly available code to generate these spectra, these secondary spectra. It uses particle physics codes as Pythia and Hasma to generate these, and we studied some particular features in the spectrum, which is the primary peak that I'm showing here, hope you see, and what we call the valley, which is this point where the primary joins the secondary. So we looked at the dependence of the energies of these particular features. And so here's the ratio of the two energies for different ranges of the black hole mass. And you see that it essentially separates the different spins, whether the black hole has spin 0, 0.1, 0.2, 0.3, 0.5, and so on. They're not very straightforward curves, and there's actually a mass range where we have to do something a bit more complicated. I can tell you about it if you want. But in principle, if we know the mass from where the primary peak is, we can distinguish the spin of the black hole more or less easily with some good energy resolution. Another idea, but this is also only valid for highly spinning black holes. Maybe I should go back and just show you that you see these other bumps in the spectrum here. These are primary photons, but they correspond to different modes. So this is the L equals 1 mode contribution. This is L equals 2, that L equals 3. So you have a multipolar structure. So we looked at how the energies of these peaks in the primary spectrum only and the intensities, they depended on the spin. And this is a much cleaner probe because see the ratio of the energies between the second and the first peak is essentially flat in the mass. It only depends on the spin, but it doesn't vary very much. You would need a very good energy resolution. The ratio of the peak intensities is actually a much better probe. It separates much better the spin of the black hole. So these two methods, the peak valley and the multipolar, they are independent of the distance to the black hole because we're only taking ratios of energies or intensities, and that's good. But this one only works for spins above 0.6, which in principle cannot be reached if you start with a very low spin, just with the axiverse, the picture of you spinning up the black holes. So our latest thing that we looked at is combining, looking not only at photons, but also at neutrinos that are emitted. We have now loads of, we have neutrino telescopes available and lots of experiments planned. And here's examples of the primary photon and neutrino spectrum and how it depends on the spin. And you see they both, the spin always increases the emission of both photons and neutrinos, but they peak at different energies and the spin has a different effect on both of them. So in principle, and we checked that the ratios of the peak energies and the peak intensities of photons and neutrinos would just depend on the spin of the black hole. So they would be a multi-messenger approach to determining the spin of the black hole. There's a slight caveat here because when you have spinning black holes, the emission is not isotropic and we're not looking at the full integrated flux, only along the line of sight. And if we don't know the line of sight inclination relative to the black hole's axis, then we can't really infer this total flux emitted. But Huber Perez Gonzalez at Durham, he made an interesting proposal that there is a dependence on this angle, on this line of sight, in the asymmetry between neutrinos and antineutrinos, and also between the two photon polarizations that could help us determine not only the spin, but also the angle, the inclination angle. Another idea is if the black holes, the primordial black holes are really close to the Earth, they're moving about 50 astronomical units per year, so they have a proper motion that we could detect. And as they move, their line of the inclination would change. So you should see a modulation of the intensity of this Hawking spectrum. And from this modulation, we could in principle infer what is the total Hawking luminosity in both neutrinos and photons. So in principle, there are quite a few ways that we can measure the mass and spin of a black hole, and that we could use it to probe the string axiverse and new physics and so on. I'll just leave you with my final slides, which are looking at the experiments that we have available and the actual spectra, the primary spectrum of photons here for different black hole masses to see how far we need to reach. So we have Fermi that's been available. Hawk has been available in all these experiments as well. Now we have LASSO coming online. I think SWGO, I can't remember if it's online already. The CTA is certainly planned. So these are high energy gamma ray telescopes. And we also have in the kind of a sub-GeV range, we have these two proposals, AMEGO and ASTROGAM, one from ESA and one from NASA, of gamma ray telescopes to probe this region. So here's a black hole that still has a mass of 10 to the 12 kilograms, so it hasn't evaporated much yet. This is the spectrum. So black is Schwarzschild, red is 0.2, spin, blue is 0.5. So we could, in principle, detect these with AMEGO if they're very close, 10 to the minus 5 parsecs, that's kind of within the solar system. These might be hard to tackle, but as they evaporate, you see the spectrum goes higher in energy. And with Fermi, you can detect them to 10 to the minus 4 parsecs, and then 10 to the 10 kilograms to 10 to the milliparsec. We reach that, so this is more reasonable to expect. And here you see the distance to which we can see these black holes is increasing as they evaporate. So 10 to the 9 kilograms, 10 to the minus 2. So now you go to the TeV scale. You can go to very large distances, astrophysically 0.4 parsecs, 6 parsecs, and 70 parsecs here. Okay, so I'm basically finished. The main take-home messages that I would like to give you is that we can use, if primordial black holes do exist, and I really hope nature has been kind enough to provide a few, we can use them as particle physics laboratories. And if we have a string axiverse picture, so an underlying string theory with hundreds or thousand axions, then these primordial black holes will have some non-negligible spin that we can probe. We can probe the total number of light axions. There could even be superradiant clouds formed for heavy axions. And we can even expect to learn a lot about new physics by tracking the evolution of the mass and the spin of the black hole in this final explosion. And an interesting thing is that we don't really need to convince anyone to build new gamma ray telescopes or neutrino detectors, neutrino telescopes, because they have a variety of scientific goals. So there's been an effort on these missions, both space-based and ground-based. So we could just take advantage of this multi-messenger astronomy era that we're living in to actually try to detect these primordial black holes. So thank you very much.
Okay, thanks for the nice talk. Any question from the audience? You can unmute yourself and ask. I can already see one question in the audience, but maybe if you want to unmute yourself and ask, or should I? Okay, better maybe if I read it out. So Shukarna from the audience is asking, if primordial black holes are formed in a non-radiation dominated era, does that lead to a different initial spin distribution? And does it affect the conclusions of the string sections from previous evaporation?
Yes, thank you for the question. So I didn't mention that much. So there's been at least one paper I know about that argued that so if the primordial black holes are formed, let's say in an early matter-dominated era, for example, if the inflaton field takes too long to decay after inflation and behaves as dark matter for some time, so the primordial black holes that would be formed in this period would have very large spins, even extremal. And the argument, just roughly, is saying that because the gas is pressureless, then the collapse, if the initial perturbation, if the overdense region is not perfectly spherical, in the radiation era, it will become even more spherical due to the radiation pressure. But in the matter era, in the absence of pressure, these anisotropies will just get enhanced. So you create a lot of angular momentum. So much, in fact, that sometimes the angular momentum would prevent black hole formation. But the argument that this paper, I can't recall the name of the authors, but I'm happy to give it to you. It's in our references in the papers. The argument is that the few black holes that form should be quite near extremality. So spin parameters